Hello and welcome to Build Your Own CPU Part 3. In this episode we'll have a detailed look at the tri-state output circuitry, the zero flag of the status register, the carry flag of the status register, and this mysterious C register. Now this is inverting tri-state output circuit. On the left you've got Q1 and Q2. They're just an inverter of the output enable control signal because Q3 is a P channel MOSFET and needs the signal inverted. So this is with the output disabled and data comes in to the inverter and doesn't go through. So it's like this. You've got the positive supply comes down to Q3 and negative supply to Q6. And because they're turned off, the Q4 and Q5 that form the inverter have got no supply, so they're just floating. So it's got high impedance output and just follows the data out, whatever value's on that. Now, if we turn the output enable on, Q3 will start conducting to bring the positive supply down, and Q6 will start conducting for the negative supply to come up to the inverter. So Q4 and Q5 that form the inverter have now got a supply. And thus the data that's coming in from the left gets switched out to the data output. That's all looks good. So now we want more than one bit. We need 8 of them. But this circuit just shows 2. So we've got data 1 and 2 coming in. Got positive supply coming down to Q3, negative up to Q6. They don't go any further because the output enable's not turned on. So there's no data 1 or data 2 output. Fine. So let's turn the output enables on. Now we've got data 1 and data 2 gets transmitted through because supply is coming through Q3 onto Q4 and 7, and the negatives coming up through Q6 onto Q5 and Q8. All looks good. We just need 8 of them for 8 bits. Yeah, well, it don't quite work out like that. I got caught with this. So imagine you've got the output enable's not on. It doesn't matter what the data in is, but the data out, that's onto, say, the data bus. Imagine data 1 has got a 1 value on it, so that's 5 volts. You'd have this scenario. But Q4 has got a body diode, and that would conduct up, and thus the 5 volt signal on data 1 becomes a supply to all the other inverter gates. It'd only be 3 to 4 volts. Actually enough for Q7 to turn on, and thus data 2 would then come on. It might only be 3 to 4 volts, but that's high enough to switch other outputs. So if you've got 8 of these, that signal would feed to all 8 of them. So your output could be anything. It could be 1s, could be 0s, because if you've got 0 there, you've got Q5 has got a body diode, so that would conduct in the other direction. So it just makes a whole mess of everything. So you can't use just 2 transistors to switch your supply on and off to your buffer. Here we have the original register circuit board. So up here we have the 2 transistors for the inverter for the control signal. Here we have the 2 power transistors for switching the power. And that's bit 1, bit 2, bit 3, bit 4, 5, 6, 7 and 8. So these are the supply to all of these outputs controlled by this signal here. We'd have to use a circuit like this where each inverter has got its own supply transistor, as in Q3 and Q9, Q6 and Q10. So if you're sitting there not doing anything and data 1 happens to be at 5 volts, that will still come through Q4's body diode, and you end up with 3 to 4 volts between Q4 and Q3. But this can't go anywhere. It won't go up through Q3 because your positive supply at top is 5 volts, it's higher. So that just isolates that signal from any of the other bits. Alright, here we got version 2 of a register output card. And this is the output. You may notice it's a bit different from the previous one. So these 2 transistors here are still inverting the control signal. And this transistor and this one are the supply transistors to this inverter. These two are the supply transistors to this inverter. These two transistors are the supply for this inverter, and so forth all the way down. So each output on the data bus going out has got its own pair of supply transistors switched by the control signal. So they're all isolated from each other. Now this is the zero register, or zero flag I should say. On the left you've got all the data's coming in. They go through 3 NOR gates, and the outputs of those go into a 3-input AND gate. So if all inputs are 0, you get a 1 coming out. Now that doesn't automatically go into the 0 flag. It only goes there if you decide you need to save it. So you've got a 0 input enable and pulse signal to switch that into the 0 flag. Now there's an instruction called skip if 0. And what that does is it skips the program counter forwards 2 bytes if you have a 0. So with that instruction, you'd have a 0 output enable on, and the 0 flag will then get fed out to D1, not D0. Now, if you're doing the skip instruction, the program counter will get fed into the A register. This signal would go out to the B register, and D0 and D2 to 7 will be held to 0. The 0 flag will be fed out to D1. Thus, the byte in the B register will either be a 0 or a 2. And you're going to add this to the program counter. So you either skip forwards 0 bytes if the 0 flag was 0, or you skip forwards 2 bytes if the 0 flag was a 1. Now here we have the carry flag. So C70 is the 7th carry flag of the adder, because it's got 1 for each bit. So it's the very last one, so it's the carry out basically. And that, if you want to save it, gets saved into the carry flag. Again, there's a skip if carry instruction, so you can output that onto D1 again. So if you have a carry, you just skip forwards 2 bytes. If you haven't got a carry, you don't skip forwards. So this is the mysterious C register. So if we go back to the carry flag, if you're doing an add with carry, then the carry flag going out would feed into the input of the adder. But then the output of the adder, you could have a carry on that, and that needs to go back into the carry flag. Well, one could be on and one could be off, and you wouldn't know which way to go. It'd keep turning on and off, or stay on or stay off, and basically you couldn't add with carry because the carry flag would be indeterminable. So what you need to do is you need to double buffer this latch, and that's where the C register comes in. So the carry flag doesn't actually go to the input of the adder, the C register does. So if you're doing an add with carry, when you're loading the A register with a value, you'd also move the carry flag into the C register here, like this. So when you're doing an add with carry, you've got the output from the C register. The adder actually adds the A, B and C registers together. So you've got whatever's in the A register and whatever's in the B register, plus the what was in the carry flag. It's now in the C register, adds that onto it. And if there is a carry from that addition, that goes into the carry flag register. Thus they're both isolated from each other. Now if you're doing an add without carry, you need to clear the C register, make sure it's a 0. So when you're loading your A register, you need to load your C register as well, so you load it with a 0. Or if you're doing a subtraction, that needs to be a 1. So you put a 1 in there instead. So this is the actual circuit of the C register. You've got your standard pulse and register input enable AND gate. And there's your input control, so if you want the carry flag to come in or not. And there's the actual memory cell made of 2 NOT gates and your feedback resistor. your weak pull-up. And here we have the clear, which is just switches to 0 volts to pull your memory cell down to 0. And here we have a pull-up to force your memory cell to a 1. Now, you'd normally feed something like this off the 5 volts and use a P-channel MOSFET to switch it in, but then your C register set signal would have to be an inverted one. And I wanted all the control signals to be positive switching. So I came up with this circuit and done this 2 or 3 years ago. And looking at it now, I can't quite see what that MOSFET's meant to be doing. I'm sure just a diode there would work just fine. But this is what we got, and it works, so I'm going to stay with it. This is the whole status register. At the top you've got the OR gates coming in, feeding into the AND gates of the 0 flag. That's a 0 flag control circuit coming in, and that's the 0 flag memory cell. And that's the control AND gate for the pulse signal. And that all feeds out here. Well, on the right you can see the 7 transistors that pull D0 and D2 to D7 down to 0, and then the output goes out of D1 to give you either a 0 out or a 2. And it goes out to the data bus, which is on the right there. Now this is the carry flag, that's the input control and the actual memory cell for it, and the control signal coming in so you can save your carry flag. And there's your output, again D0 and D2 to 7 are pulled to 0 volts, and your output goes on to D1 to give you a 0 or a 2 output. And down there is the C register, which we just saw in detail. Now this is the status register board. So we've got all the control signals coming on the left, quite a few on this board. Here we have the usual decoupling capacitors and the magic blue smoke resistor to limit the current to all the rest of it. So these here, all the NOR gates and AND gates for calculating the 0 flag, which gets fed back down here into the input to the 0 flag register. And there's the actual memory cell itself to hold it in there. This is the AND gate at the beginning to control whether you want the signals to come in or not. And here we've got the output signals from it feeding out up onto D1, and these 7 transistors, they'd hold D0 and D2 to 7 at 0, so you'll either get a 0 output or a 2 output from that goes onto the data bus. Here we've got the carry flag, very similar, except the carry is coming in from over here, and that's the part where it switches in. And there's your AND gate at the beginning to control the switching of this circuit to put into the memory cell here with the C register, carry flag rather. And there's your output switching on to D1, and these 7 transistors here are to pull the other bits to 0 as well. So again, you've got a 0 or a 2 coming out. And this down here is the actual C register. So the carry flag from there will actually be switched into here. Again, with there's your AND gates in the pulse for controlling the actual input, and there's the actual memory cell sitting in here. But this one's a little bit more complicated because you've got a pull down MOSFET for pulling it to 0 and a pull up one for making this a 1 for when you need it to set it to 0 or 1. The output of this doesn't come over to the data bus at all. It feeds back across out onto the control bus, so there's a C register output up here that goes out. If you bring over the board for the control signals, so this is the control one. So above here you'd have all the control signals, and they would feed down onto this board and then link across to the relevant one. So this board is used on lots of different cards, so there's lots of options, so you just pick the ones you want, the control signals. So the C register will come back up and come up here. The C register doesn't actually feed onto the data bus at all. It goes back out on its own control signal dedicated to go to the adder. So this would also be on that side, another one. So your data comes down here and will feed through out the bottom to other registers, or there's your data bus there, so you can connect links straight across there. So I think that's enough for this video. So don't forget to like and subscribe, and hopefully I'll see you in part 4.